Okay, now this section talks about a little puzzle that involves permutations. But in fact, it's going to help us understand some fundamental ideas about permutations, in particular how they relate to two cycles. All right, so here's the picture here. So in this case, I have a 12-car switchyard. So here's the train. The train has 12 cars. It comes into the switchyard and fills up the 12 positions. Okay, so then when the train is finished, then the train can go out again in the same order. All right, now once you move the train in here and the cars occupy these positions, then you can switch cars. You can switch the two cars in these places. Okay, so for instance, when the train first comes in and the first car is here, second car is here, third car is here, and so on, I can switch these two cars. Okay. Now suppose I wanted to switch cars 4 and 5. What I could do is then I could move the train around until 4 and 5 occupy these two places, and then switch these two cars there. Suppose then I wanted to switch cars 8 and 9. Well, then I'd move the train around again until 8 and 9 occupy these two places, and then I'd switch. So what am I doing? I'm either doing a 12 cycle. Whenever I rotate the whole train, I'm doing a 12 cycle. And then when I'm switching two cars, I'm doing a 2 cycle. Okay, so I'm doing either 12 cycles or 2 cycles. So let's write those two permutations in this way. Let's say R is the 12 cycle, and S is the 2 cycle that switches the two cars in these two positions. So the question is, using these two permutations, how far can I go? Can I rearrange these cars arbitrarily? Suppose I want to reverse all the cars, so instead of 1, 2, 3, blah, 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 up to 12, I want it to be backwards. 12, 11, 10, 9, 8, etc. I want to, or suppose I just want to switch these 4 cars and leave the others the same way. Can I do any arbitrary rearrangement of the cars using just this switchyard? Okay. This should remind you a little bit of the dihedral group. Dihedral group, we had rotations and we had flips. Now a flip is not the same as a 2 cycle. If you go back, you'll see that a flip doesn't just switch 2 positions, but it switches all the positions in the figure. But the idea is the same. Here we have 2 basic permutations, and we're trying to get all the permutations in terms of these 2 basic permutations. All right, now, for instance, I know that I can write the permutation 1, 2 is S. Okay. Unfortunately, it looks like there's a misprint here. This should be, instead of S, this should be T. Looks like it's called T in the subsequent parts. So these should be T here. Okay, see, you have T here. Okay, so let's look at this particular exercise. Okay, now let's take a look at one of these. I'm calling the rotation 1, 2, 3, 4 by R, and the exchange as here is 1, 2. Now how would you write 2, 3? Now to get 2, 3, what do you do? Well, to get let's look at the cycle here. 1, 2, 3, 4. Okay, and here's my switch here. If I want to switch 2 and 3, I'm going to have to rotate backwards so that 2 and 3 are here. Then I'll switch 2 and 3, and then I rotate forwards to return the 2 and 3 to the same position. See how that goes. Here's my original. This is my original. then if I apply R inverse, now R inverse, that's the same thing as R cubed. You can think about that. If I apply R inverse, then this becomes 2, 3, 4, 1. Then if I apply S, it's going to switch these two. So that's going to be 3, 2, 4, 1. So this is, I'll call it R cubed, and I call this S. And then if I apply R forwards again, I'm going to get 1, 3, 2, 4. All right, so that's how I got this first one. Okay, so I could write 2, 3 is equal to, now remember I did R cubed first, so R cubed goes on the right. Then I did T second, and then I did R. Okay, so I was able to express this as powers. Now you should be able to do the same thing for 3, 4. Think about what we did here. We rotated, then we switched, then we rotated back again. Right? Right, now it turns out that you can build up these operations to get these. Let me give you a little hint on this one. To find this permutation 1, 2, 3, if you think about it, the permutation 1, 2, 3 can be written as, I think it can be written as, well, let's see if it can be written as 1, 2, and 2, 3. Let's see if that works. Okay. Well, if I put 3 in, if I put 3 into this permutation, 3 goes to 2, and 2 goes to 1, so that works. If I put 2 in, 2 goes to 3, and if I put 1 in, 1 goes to 2. So, in fact, this is true. So you can use this fact to find the representation of 1, 2, 3 in terms of R and T. I'll give you another hint. We already have a representation of 1, 2. That's T. And we have a representation of 2, 3. We got that from part A. So that's how you're going to get the representation of this 3 cycle. Okay. So this exercise builds on itself. You're building permutations. Here you're building consecutive 2 cycles. Here you're building consecutive 3 cycles. Here you're building the inverses of those consecutive 3 cycles. Then here you're building non-consecutive 2 cycles. And once you get all the transpositions, you get any permutation. So you can think about why that is. So here we did it for a switchyard with 4 positions. Now we consider the case for a switchyard with n positions. All right, so we do the general proof for a switchyard with n positions. So what this means, in short, is that the 2 permutations R and T generate the group Sn. I can write any permutation as a product of these 2 permutations. It could be a complicated product with some R's, some T's, some R's, some T's, but any entry of Sn can be represented as a product of these. Okay, so we'll stop there.